industry research, short for AIR, Tsinghua University. And in this lecture, so I will talk about the data-driven methods for intelligent urban transportation systems. It seems I started already. Okay. Okay, let's begin. Okay, so this lecture will talk about how do we design data-driven methods to solve some of the urban transportation problems. Especially we are looking at how to use some of the data engineering and AI method and to address some of the commonly available urban transportation problems. And what are the design philosophies behind these systems? And what are the future perspectives? And so this is the, not working? Okay, so this is the agenda for this lecture. So I will first describe some of the emerging data sources for urban transportation problems, and especially what are the characteristics of the spatial-temporal data, and what are the modeling challenges. And the second, I will introduce a series of data-driven transportation applications. Specifically, there is one example for how do we monitoring traffic states, how do we reliable forecast the traffic conditions in the future, and how do we perform data-driven planning. And the last one is a little example on how do we use data-driven methods for operation management. And I also talk about some of the future perspectives and how do we use this kind of data-driven method to solve some of the future problems. And so let's first talk about the data. So because this lecture is about data-driven methods, so data is everything. And that's at about 2 decades ago. So in these 2 decades, so because of the development of ubiquitous computing and some of the mobile technologies, we have massive amount of self-generated data that are generating every day in the urban space. And to give give you some numbers, and for example, in the urban sensor networks, a typical example is a license plate recognition camera on the intersections. Even for a small city in China, so there could be as many as 40,000 vehicle records that pass in the intersection in a day. And back in 2013, and if you look at the New York City, and you will get about 500,000 taxi trip trajectories in a single day. And right now we have more of the e-hailing services like the Uber and Didi. And we now even have more taxi trajectories generated every day. And another big data source is the mobile phone data. And for example, in Suzhou, in the city of Suzhou, in just one day, there could be as many as 200 million mobile phone records that are generated one day. So that occupies a space that about 23 gigabytes. And there is also a lot of other data sources that can be used to solve transportation problems. For example, the smart car data for buses and for subways. And also, right now we have the ride sharing services, and we also have a lot of bike trajectories. This can also be used to solve some other interesting problems. And I think another very potential and important future data sources is the sensory data from the autonomous vehicle. And this can be a game changer to change a lot of things for future intelligent transportation systems. And so let's look at a short video. So this video basically shows the trajectories from the taxis, buses, and trucks. How do I get rid of this one? This basically shows the variation of trajectories from taxis, the trucks, and the buses over the single day in Shenzhen. You can see the very dynamic pattern that changes, evolves over a day, and from morning to evening, that captures the rhythm of the city. And also you can see there is actually a massive amount of vehicles and also the highly complex dynamics that keep changing in a single day. So this contains a lot of information. And for the first time in the history, basically, we do not need to rely on building analytical models based on assumptions, but rather we're directly using this data. We can directly observe how the system actually works and what are the dynamics inside the system. So that actually changes a lot of things. So basically, if you there is a lot of modern transportation applications that are already powered by the big data, and in other words, they are already data-driven. And one of the most commonly used services are the online digital maps. For example, the Google Maps, the Baidu Maps, and the Gaode Maps. So usually, currently nowadays, all these services, they have some kind of data-driven traffic state estimation or traffic state forecasting algorithms running behind. They keep collecting the trajectory information from the user's devices and use those fresh information to update their traffic state information. And they can use this information to provide routing and navigation and then a lot of other provide a lot of other travel information to the users. And about 2 decades ago, so most of the transportation planning is not data-driven. So the traditional way to do that is to find a lot of people and conduct a transportation survey. Basically, we ask a lot of people to fill a lot of questionnaires. They ask questions like, where do you live and where do you work and how long do you commute for work and which mode of transportation you use to do this commuting. And but right now, so we do not need to rely on this kind of surveys. We directly use the data we have to see what exactly are the traffic flows coming from one place to another place in the city. So actually, this is much more accurate and can make more reliable future planning for our systems. And since we get this amount of data, so basically we get a good understanding about the current condition of the entire system. So in that case, we can do better traffic management and control, and we can do better congestion relief, and we can also detect the accident in the road network early, and conduct early intervention. And if we know the road speed and the volume, traffic volume on this road for every link in the network, we can also compute the vehicle emissions, the network-wide vehicle emissions. And this can also be used to help us to improve some of the infrastructures to get a greener city. And recently, there is also a lot of studies that trying to borrow data-driven methods to solve the signal timing optimization problems. Although this problem right now is not fully data-driven, but there is some very good progress. They trying to use data-driven methods to estimate the volume traffic demand on the intersection and use some of the transportation engineering tools to optimize the signal control to minimize the signal intersection delay. So basically, we already have this kind of data-driven applications. And there is also a clear shift from the previously engineering-based method to the data-driven based method. And the thing or the data behind this kind of applications is what we call the spatial-temporal data. We call it spatial-temporal data because the data contains both the spatial property and the temporal property. And we can basically classify all this kind of spatial-temporal data in the city into 6 categories. Depending on the data structure, whether it's a point-based or network-based, and we can classify them into these kind of categories. And the most simple type of the data is actually the POI, is the spatial-temporal static data. So everything is static. A typical example for this is the point of interest data on our online digital maps. So point of interest data means the venue labels on your online digital maps to suggesting whether this is a restaurant, whether it's a hospital, whether it's a school. So it's just purely static data. And we have a lot of fixed sensors in the road in the city. For example, the license plate recognition cameras. So these are the spatial, static, and temporal dynamics data. So the location is fixed, but it keeps generating time series readings. and it provides some of useful temporal information. And another more complex data is the spatial and temporal dynamic point data. So a typical example for this kind of data is the social media checking data. For example, when you're checking on Weibo, the Foursquare and Twitter, so basically you will generate tweets with a geolocation attached. So these are typical examples of the spatial temporal dynamic point data. And if we look at a more complex type of data, the network-based data. So the simplest one is the spatial temporal static network data is the road and the transportation network data. So data contains somewhat complex topologies. And if we overlay the traffic states onto the road network and we inject the time evolving the traffic states, then it becomes the spatial static and the temporal dynamic network-based data. And the last one is, and also the most informative but more complex one is the trajectories. So these are the spatial temporal dynamic network data. It's a series of ordered points and with both timestamps and also the geolocations. So these are the most commonly used data that we usually use for data-driven transportation modeling. And so this kind of the spatial temporal data has some unique characteristics. It is different from the image data, text data, and all the other data that we typically encounter in the field of data science or AI. So basically because it encodes both spatial and temporal information, so it has some spatial properties and also the temporal properties. For the spatial property, I think the most important property is the distance, the notion of distance. So the 2 points, if they are close to each other, then the functions behind these 2 points are most likely very similar. So that is the first law of the geography. And for example, the two adjacent road segments may possess similar traffic state conditions. And also we have the triangle inequality. So this has very important usage in the applications like routing and in other things. And also we need to consider hierarchy. And because if you aggregate your spatial temporal data to different granularity, you might get very different results. For example, if you aggregate into the district level, or you aggregate to the zip code level, or the road segment level, and if you run the same analysis, it is likely you get very different results. So basically, granularity is very important if you want to design a suitable application using this kind of data. And also we have the city structures behind. So because in the city, we have the road network, and also we have the functional regions in the city. So these also have important impact on the patterns that you observe in the data. And also it's like we also have the temporal properties, and basically it's the temporal closeness, which is similar to spatial closeness. The 2 timestamp is close, then most likely the functional behind this is very similar. And also we have the periodicity. For example, in every day we have the morning peak, we have the evening peak, and at night. Also have the trend. So trend is a long-term pattern that occurs in the temporal data. For example, if you go through when it comes from summer to winter, as the day gets shorter, so people tend to go to work later. In that case, if you look at the same time period, in this one is 9 to 10 a.m. So we'll see the road condition actually get better because people goes out late. So what are the challenges to leverage and build applications using this kind of urban big data? So there are several. The first thing is like the big data itself is a problem because of its size. This is a toy example. For example, if we process the trajectory data of an entire city into an image frame, so a single image for 1 minute interval will occupy a space of 6 megabytes. And if you accumulate the data into the whole year, so occupies a space of the 3 terabyte. And if you do this for maybe taxis, buses, trucks, and even other mode of transportation, and it can takes the space of about 9 terabyte for a single city. And if you want to provide a service for about 120 cities, and it will take a space of 1 terabyte. So this one basically is already beyond the capacity of some data centers. So, and also it's like this large amount of size of data also cause a lot of problems, how we model and how we solve the problems. Traditional method won't work, but luckily we have some of the new method like the deep learning approaches and some of the other data-driven approaches. So we still can get a relatively scalable solution while fully utilize the information in this kind of data. So the other challenge here is the complex and highly heterogeneous spatial-temporal patterns in the data. So this can cause a lot of trouble when you model this data and to solve some problems. For example, the figure on the left, on the upper part. So this is the vehicle trajectory points at 6 a.m. in the morning in a very small region in Jinan. You can see the trajectory point only sparsely covers the region. And in a lot of roads, there is not even a single trajectory point. Basically, you get nothing. You get no clue of the actual traffic condition on this road. But if you look at the evening rush hour, so it's like the 17, it should be p.m. In a small region, and a similar region of the Jinan. So basically, every road are densely covered by the trajectory points, and you get a lot of information. So although we get a lot of information, but the distribution of data can be highly heterogeneous in space and time. So that causes a lot of sparsity in several parts of the data. And you need to build a model that is robust enough to overcome this kind of complex pattern and also the highly heterogeneity in the data. And another challenge here is like in most of the data-driven applications, we need to somehow use multiple sources of data to improve our model accuracy or make our model work. For example, you might need to use the mobile phone data. You need to use the vehicle trajectories. You need to know the meteorology information, like weather information, in order to achieve some of the accuracy. And it is important to leverage this very different structure of data, or different source of data, and use this information from these multiple source of data to build a model and solve problems. So this is another challenge. So you might ask if there is a working pipeline or workflow for solving or developing these kind of applications. Luckily, there is. Yes, we have. At least we have right now have a working solution. So basically, it can be structured this way. So we first need to use urban sensing technologies to extract the information from mobile devices, and these are the base of your work. And so you gather the information from the data from the mobile devices, and you need to also have to use some of the data management tools or libraries to solve this problem. For example, in order to handle this kind of data, you need to first use a proper data structure. You need to develop highly suitable spatial-temporal indexes to make the data processing fast. And also you need to consider distributed storage and the computation. Once you're dealing with the data, then you need to develop some of the data analytics models and even some of the deep learning models to use this data to extract the raw information from the data and turn into some kind of knowledge that you can use to solve and to support some of the upper level applications. And basically it's a marriage of the transportation domain knowledge and also the data science and AI. And you need to use the domain knowledge to guide the model design. And also you need to use some of the state-of-the-art AI method to help you extract information from the data and do something useful. And you also need to use the cloud computing to handle the large-scale data and also providing the services. So next, we will introduce some of the data-driven transportation applications, and I borrowed this lamp. Data is all you need. So this one, if you are working in the field of AI, so this is something like it might be a joke, yeah. But the reality is this. So when you are developing data-driven transportation applications, so data is all you need and all you can trust. And you try to avoid making assumptions and use the knowledge from the data to achieve your goal. So the first problem we're going to look at is how do we estimate the traffic space for the entire city, for the entire road network. And this is a very important problem for many online digital map services like the Baidu Map. So for every this kind of services, there is some very large-scale algorithm running behind, keep collecting the real-time information and update the traffic status for each road. And usually they use the mobile sensing data, like the data from mobile phones or the vehicle trajectories. Although this is already a working system, but this problem itself still has a lot of challenges. The first two challenges we already talked about, like the complex spatial-temporal pattern and the data sparsity issue caused by the highly heterogeneous pattern in the data. So the data unreliability could be an issue to provide a reliable service. So there is a very interesting case that there is one mobile online digital map service user that intentionally driving very slow on the road. And this road has very light traffic, almost no other cars. But they intentionally drive very slow, and produces a very slow-moving trajectory. So since there is no other trajectories, so this erroneously generated trajectories actually tricked the algorithm behind this online digital map service, and make the system think this is a highly congested road, since it's moving very slow and it believes this may be a very congested road, and so it provides wrong routing recommendations for a lot of other users, and because they think this is slow, and they guide the users to go from other routes. So this is a typical example of the data unreliability caused by the data sparsity and some of the errors in your data. So it is desirable to introduce some of the interpretability and estimation confidence on the results. And also, of course, once you're providing this kind of services, you need to make your application algorithm scalable and can run in real time. So we can actually cast this problem into a missing data imputation problem on the graphs. So if we abstract the road network into a graph, and with the node represent each road segment in the network, and the adjacency between different road segments as edges. And we can also overlay the traffic states. For example, in this case, is the traffic speeds as a feature on each node. So once you overlay all the trajectories you have in this time period, so you will get a partially filled graph. And our goal is actually to predict and fill the missing entries in the graph that is not covered by trajectories or contains erroneous information. So the overall framework is working like this. So you'll get a bunch of trajectories, you'll get a road network, you first perform map matching. So basically you map the road trajectory points into the network. So every trajectory points will be bound to a road segment. And then you compute the route traffic speeds road speed graph. And so you get a lot of unknown entries, missing entries. Then you need to perform spatial-temporal imputation. The way we do that is we first extract the features, spatial-temporal features, and then we join the link tree models to reconstruct the partially filled data and make it into a filled graph data by exploring the aligned patterns in the data. and also jointly train another discriminator, which is the confidence estimates for each data records. So this is actually the model. So it's basically a very big neural network model, deep neural network model. So the traffic speeds are formatted as a graph, and each frame is a one-time step. And we also have information, the support information. The support information basically is the number of trajectories that are appear on a specific road segment. So basically, the better support you have, the more confident you will be for these estimates. And so the reconstructor's purpose is to use this kind of information to construct field neural network speeds, and also we introduce another model, which is the discriminator, which takes the same input, but with this field results also serve as to detect, to output the reliability of each field entries. And so this information will also be used to help the reconstructor to learn better. So I will skip the details, and so this is the results. So this is actually a very strong model and very robust. And so the red bar in the first figure actually shows the error rate of our method. So you can see even the missing rates of the data go from 30% to 70%. And the error still remains relatively low, while the other state-of-art method, the error increases rapidly. I think the best part of this model is that we're not only imputing the missing traffic states on the road network, but also we gave them the estimation confidence measures, the P here, to each record. So you can see there is a road segment C there, so marked in the blue, and it is obviously some kind of the problematic data, because the upstream the road speed for upstream segment and the downstream segment, the speed of them is around 10 to 20 meter per second, but this one gets the speed of over 50. So that is definitely not possible, and it is actually likely generated by a speed vehicle. So that's not to represent the true traffic condition. And our model actually can tell this one is not reliable, give them a very low confidence that P equals to about 0.3. Yeah. So with this kind of information, we can build a more robust travel information system and provide more robust routing. So the second demo I will show here is like another interesting work from the TsinghuaUni 2017. So this work is actually to focus the crowd flow in the city, and this also has a lot of important application in the city. For example, we need to use this one if we know the crowd flow traveling from one part to another part of the city, and we might need to be it will facilitate us for better transportation management and to avoid some of the extreme cases like the overcrowding scenarios, and also helpful for guide us for better future planning. And this is also a very challenging problem because it is impacted by a lot of factors. For example, this kind of the crowd flow is definitely impacted by previous time interval, the flow in the previous interval. And also it is both impacted by the nearby regions and also the distant regions, because people might go from home to work, and the workplace might be far away from his home. So they have this long-term, long-distance dependency in your data pattern. And also the weather condition and the traffic control measures and also the rare events also have very huge impact on the traffic flow you observe in the data. And of course, we have very complex spatial-temporal properties we have just introduced. And so this is actually how they do that. How do they solve the high accuracy traffic flow forecasting problem? And their approach is very interesting. let's see how they do this. So the first step is they first segment the city into a uniform grid cell 1 kilometer by 1 kilometer, and they actually cast all the trajectories into each cells of the region. So, and they count the total inflow and outflow for each cells of the entire region. And this gives you image-like data, and which with each pixel represent one cell. And also the color of the image represents among whether it's have a lot of flow or have very few flow. And once you have this, and you can do this for each time frame. And you also have some of the other information like the weather and like the events and something like that. So basically you convert the traffic flow forecasting problem into image prediction problems. This is very interesting because once you have this, you can use a lot of advanced image processing models in deep learning literature. And basically, if you get a lot of this image by image input of different time period, and we can use convolutional deep neural networks to track the feature from the recent few steps. You can also do it for the same time period in a week, and you can also do it for the same time period for last month to capture the long-term dependency and the trend and also the periodicity. And you can also fuse this kind of the extracted information as well as some of the features like weather condition and events and something like that. Once you fit all the information together, so, and you now can capture very well the spatial-temporal properties of the data, as well as the external influencing factors, and you can make very high accuracy traffic flow forecast results. So this is actually the system they built, and this is in the city of Guiyang, and so the color here is the amount of flow in the region. The black curve here is the ground flow, and the blue curve here is the historical flow predicted by the model. And the green curve there is actually the forecasted flow. We can use this capacity model to predict what are the change pattern of the flow in the future. And imagine if there is a concert in a city, and which draws a lot of people there, and we can use this model to tell whether there is a crowded risks there. And if there's such a risk, then we might need to introduce some of the intervention strategy. And in many cities, it is not suitable to segment the entire region into uniform cells, but rather it's like we have irregular shaped regions, and we have the zip code segmentation of the entire city has an irregular shape, and sometimes we want to know the inflow of the outflow of this in this kind of irregular shaped administrative area, and we can use a similar strategy to develop model to perform the traffic flow forecasting process in this kind of irregular shaped regions. The key here is like replace the data into a base data. So for each of the irregular shaped region, we can place Detroit there, a single node there to represent this region, and we also carry the inflow and outflow information, and we can this node is nearby nodes, and this will give you a graph for each node, and this graph actually represents the total amount of flow and in and out of the region in the current time step, and you can build a lot of this kind of graphs time step by time step. You can use the temporal data extraction and the modeling method to process to input the data from the recent time periods and also the big data and the weekly data and the monthly into the model. This time we are not using the image-based neural network layers to handle this kind of data. We use the graph convolutional networks, which is the learning neural network work on graphs. Use this kind of approach and as well as to and as performing data fusion to get the output, and use this to predict the future traffic flow. So this one is like a very good example of how we build highly customized structures to help the structure. Completely interesting study conducted by one of when we do planning, so basically it involves a lot of human knowledge. And I won't say it is wrong, but sometimes it's not accurate enough. But right now, since we have the ride-sharing services, and we can accumulate a large amount of sharing bikes trajectories, and we can directly use this kind of information to facilitate us developing highly reliable bike lane planning strategies. And I think in the past, so there is a lot of people in the city, but since the growth of the economy and also our living standards, a lot of people actually stop biking more. But recent years ago, so there's the emergence of the ride-sharing services, and people start again. But when they bike again, they find the bike lanes are already gone. They either change to the drive lanes or they are occupied by the parked vehicles. So sometimes it's useful to reconsider building new bike lanes. But this is also a very tricky part, because in many well-established areas, if you want to build a bike lane, then you will need to replace a drive lane. And in other cases, your budget is limited, so you cannot build unlimited length bike lane. So in that case, we need to find a smart method to cover most traveled roads, also maintain some of the continuity. Since you don't want to bike a while and then there's no lane anymore, and then go to another place, bike lane continues. So we don't want that. And also, it's like our budget is limited. So basically, we want to solve this kind of constraint optimization problems to find the best strategy that has the biggest coverage and while satisfy your budget constraint. So this is how they do it. So of course, you first need to get a lot of the trajectory. And what they do first, once you get this kind of trajectory data, you have some kind of heat maps like this. So this basically shows the density of the bike trajectories in this region. So once you have the trajectories and you have the road networks, and you need to do some of the data pre-processing. The first step is to filter the data, to remove some of the unavailable data, like the arrows and some of the outliers. And then you need to map all the trajectories into the map matching. And then you need to actually construct the inverted index for other computation, faster processing in the future part. So basically, this is a mapping between those segments to a set of traffic segments. And so in that case, once you want to, if you do later data analysis, you need to, once you identify one road segment, then that will help you to map it to find the trajectories that belongs to covers this road. For the part, so basically they introduce two strategies. One straightforward strategy to use a topic initialize the gradient network expansion. So what that means? So basically, it's like you have this kind of map. So it picks the most traveled segment. You use this as the initial segment, and you use a gradient network expansion strategy to keep grow from this initial segment until you spend the budget, which is allowed constructed bike lane length. So this one actually is working, but has some drawbacks. For example, maybe in this area, in this area, there is few roads that are most covered. So it will happen in the case that this top K road segment might straight into a region. That is not desirable. So another approach is to first perform clustering to cluster this kind of trajectories into different clusters, and for each cluster identify the top most traveled road segment and use that as initial segment. Then we do it again with the gradient expansion strategy to make the plan grow with this initial plan and until form a continuous good covered bike plan. So this is a very good example of how do we use data only to do without any other options. And we're also trying to solve a constraint optimization problems to make it a very scientific planning. And I think they have a pilot project for this in the city of Shanghai. And they actually collaborated with a mobile bike. Right now it's already occupied by Meituan. And they actually built a system for this. So it's very interesting and a very cool fact. And the last application I want to introduce is how we use the same bike sharing data to actually do something different to, for example, for operation management. And what they do is like they use the bike sharing trajectories to locate illegal parked vehicles. So it's you think about it. So you have the bike trajectory. So it seems nothing to do with the illegal parked vehicles. But that is actually the beauty of data-driven method. The logic is here. So because the bikes are riding on the two ends, two sides of the road. So if there is a road that is not allowed to park in a vehicle, but at some time there is an illegal vehicle there, then the trajectories, the trajectories traveling along this road might get perturbed. And if you identify these perturbed trajectories and get a lot of evidence, then it's likely that you can actually spot this kind of illegal parked vehicles. And so this is a logic, very intuitive and very simple, and connect the data with a seemingly unrelated application. And this has a lot of benefits because previously when you try to locate the initial illegally parked vehicles, you need to have some police officers patrol around, and also you need to install a lot of sensors which are very costly. But you use this kind of data, basically the data is free, and you did not need to install any new infrastructure, and you achieve it and very cheap, and also can be a very powerful approach to cover a very big area. So this is how they do for this application. So the first part is the same with our last application. So they also do a lot of bicycle data trajectory pretty precisely. But the later part is to solve an anomaly detection problem. And what they do is they first aggregate all the trajectories and also use the road geometry to build the baseline trajectories. Basically, this is some trajectories that of the bicycle trajectory should look like. And we also have the normal trajectories, and for the illegal part, the perturbed trajectories, this is very likely it is perturbed, which is very different from the baseline trajectory. And we can compute the difference between the perturbed trajectory and the baseline trajectory, and the difference we call shifts here. Basically, we can compute the shift for any trajectories that we get, new trajectories we get. And in order to compare different trajectories equally, so they also use some of the trajectory features extraction, introducing the trajectory feature extraction strategies. For example, they divide the whole road into uniform segments, and for each segment, they compute the average shifts. And they also compute the maximum shifts that are from the base trajectory. Once they got this, they run a statistical-based test, which is Smirnov test. Okay. Should we rest for 5 minutes, or should we continue? Okay. And so we can use this kind of statistical test to actually validate if there is either two data, for example, the illegal part of the trajectories or the normal trajectory belongs to different distributions. And if they have a very large deviation, then we have the reason to believe this is not similar, not something like the normal trajectories. Maybe we find an illegal part of the vehicle, and they can identify something like this. So yeah, so basically they can use this one to spot what are the high risk areas that can contain illegal parked vehicle. Yeah, so this is a very interesting application that use similarly unrelated data to solve very useful problems. And that is also the beauty of the data-driven methods, because you get a lot of data and you extract the knowledge from data, and you can support a lot of different applications. And so I think that is the 4 applications that use data-driven methods to solve the traffic state estimation problems, prediction problems, planning problems, and operation management problems. And lastly, I want to discuss some of the future perspectives, which are things that are not here right now, but might have a lot of potential and impact to our future intelligent transportation systems. The thing that I want to talk about is this one, is the autonomous driving vehicles. Remember, in our previously discussed applications, we use different data sources, like the trajectories, the mobile phone data, and bike sharing data, bike trajectories. But this data only captured information from this individual player. For example, the vehicle trajectories only contains the information of the target vehicle. We know nothing about the surrounding area. But the autonomous driving vehicle is different, because for a typical vehicle, it might be equipped with a dozen sensors. You might get lidars, you might get cameras, you get radars. And of course, you have GPS devices to track. But once you get this kind of information, you will not only know that it has a perfect understanding of what's surrounded. And for example, if you just take other data from the autonomous vehicle alone, you'll get something like this. And the green box here are the vehicles, and the red boxes here are the pedestrians. So even a single vehicle traveling around the street, you perfectly knows everything. You know all the other vehicles, what are their speeds, and what are the traffic volume, and whether there is a lot of pedestrians, whether there is a lot of other things, what are the complex environment conditions. You know everything just from a single vehicle. So so you can basically treat the autonomous vehicles as a super sensor that contains lots and lots of information. And if you have a lot of this vehicle traveling around the whole city, then basically you can build something much different from our current intelligent transportation systems. So this is only one example. Once you have a lot of autonomous driving vehicles traveling around the city, and you have the necessary V2X, which is a vehicle-to-vehicle infrastructure. And basically, you can if you fuse all the information, sense information, and information together, and introduce some of the control optimization algorithms here, and you can basically properly coordinate every passing vehicle that in that passing intersection. And if you design the algorithm well, basically you can completely remove the signal light, and no vehicle need to stop anymore. They just follow a planned path and traverse through the intersection. And this way you can maximally increase the intersection throughput and increase the entire system efficiency and even improve the safety of the system. And since you also get rid of the unnecessary braking, acceleration, deceleration, etc. Since you already reduced many of these unnecessary braking and acceleration, deceleration, so you can also reduce a lot of vehicle emissions and also save a lot of energy. So this is just one case. Once you get information something like this, so everything will be different. This data is much better than the existing data we have, and we can use this one to build very powerful data-driven applications to optimize our transportation systems. And so actually there is another very promising area I want to talk about. So basically it's to, which is currently not there yet, but I think once we get the data from different transportation systems together, and we have some new models, and we can do the customs. So basically, the current transportation system is a typical example of complex coupled networks. It has a lot of different network subsystems, like rail network, bus lines, subways, and taxi services, and bike sharing services, and also involve a lot of participants, and like the pedestrians and transportation service providers. And the system has its own data sources. And for this kind of complex networks, there is one mysterious and very complex phenomenon called cascade failure. So basically, if there's one attack happened on one subnetwork, and this failure causing some kind of failure, this failure will propagate not only within this system, but will propagate to other systems via some dependency links, and the failure will keep propagating and reinforce across different network layers, causing the global failure. So this is a very interesting phenomenon, complex networks, and so very hard to solve. And if we want to optimize the system efficient system, and also design a very robust system that can resilient against those kind of system failures, we need to jointly measure and jointly model the coupled system together. So this basically requires to take the data from different sources and use a new model that can jointly handle the problems and dynamics in each system. And, for some typical applications, for example, we do highly accurate traffic flow prediction. And previously, we predict on one system, but it's not sufficient because the flow can come from the, for example, the traffic flow can come different, transform from different mode. If you just look at one system, that uses a lot of information, and also we do collective anomaly detection and we can do coordinate control across different transportation systems. Also, we can do efficiency management and better evacuation strategies. So lastly, I want to conclude with a slide. So basically, for data-driven transportation system modeling, this is a very highly multidisciplinary area. And probably if you want to work on this area, you need to have a slightly different toolbox. Of course, you need a lot of things about transportation engineering and automotive engineering, and you need to get a pretty good domain knowledge for this one. Also, mathematics and statistics optimization are different. And more, since you are dealing with a large amount of data, you need to build data-driven models. You also need to know a lot about data science and artificial intelligence. So these are the combination of these three will give you an edge to actually define very deployable and high-capacity models that can solve real problems. And since we have showed in some existing data-driven applications, you can find there is no universal modeling approaches for these problems, and the detailed model we use are highly dependent on your problem and your data. And it is very important to know your data well. You need to know what is the property, what are the strengths, what are the weaknesses of your data, and you need to use the data property to design the most suitable model to solve your problem. And you need to find some way to maximally extract useful information from the data and do necessary data fusion. I think last and not least is the suggestion is to gather enough NA model assumptions. So data-driven studies, the assumptions are bad. Especially if you're working on a complex system, human knowledge is not sufficient, which could be in many times biased or inaccurate. So the more assumptions you make, then it is likely you will get a very poor model. So what you need to do is to let the data speak for itself. If any, if your model, you're missing several parts in order to make a model work. If any cases, you need to make these assumptions and try to get these assumptions supported by our data. So that is very important. I think that's all, and we will use the remaining time for questions.